So welcome to the 7th class. Last time we introduced convolutions with the idea of having these technical tools to be able to prove the fundamental lemma of calculus of variations and the Dubois-Reymond lemma in the LP setting. So just briefly to recap, given two scalar functions u and v, the convolution between u and v is defined as with this symbol here, u star v, and so this is a new function which whose value at x is defined as this integral of u evaluated at x minus y times vy, and this is integrated with respect to y, where this y here is the one-dimensional Lebesgue measure. And to ensure that this quantity is finite, to ensure sufficient condition for this quantity to be finite, we looked at the Young inequality, which said that if u belongs to L1 and v belongs to LP for any p between 1 and plus infinity, then the convolution between u and v belongs to LP, and this estimate holds, and this is called Young inequality. So the p norm of the convolution can be bounded by the one norm of u times the p norm of v. And last time we saw the proof of this theorem. So let's move on to new topics. So an important notion that we need is the one of support for LP functions. I mean, why do we require a new definition? This is because LP functions are actually not functions but classes of functions. So the classical definition of support that we introduced for continuous functions, which was the closure of the set where the function was non-zero. So that definition doesn't work in this setting of classes of equivalence, as we see in this example here. For example, take u to be the characteristic function of the rational numbers. So this means that u is equal to 1 if x belongs to the rational numbers, and instead it is equal to 0 if x is not a rational number. So you know that the Lebesgue measure of the rational numbers in R is 0. Therefore it means that this function here belongs to the same equivalence class of v constantly equal to 0. Okay, because this is 0 in R minus q, and q has measure 0, so basically we can change it on the set q, and we still are in the same measure class, and we chose to change it to value 0 in this class, and defining this new constant function. So these two belong to the same equivalence class, and let's look at what the support is for with the classical definition. So in this case, the support of u is the closure of all the points x in R such that u is non-zero. But by definition, u is non-zero if and only if x belongs to q. So this set here is the closure of q, and the closure of q with respect to the Euclidean topology gives R, because I mean q is dense in R. On the other hand, the support of v is empty, because there are no points where v is non-zero. So as you can see, these two functions are in the same equivalence class, but their supports are very different. The support of u is the whole real line, while the support of v is the empty set. And to fix this situation with the supports, we define we define a new kind of support, which will be independent on the representative we choose in an equivalence class. Okay, so let's look at the formal definition. And we define it for functions on RD, although we will never need this, but it doesn't matter, so it doesn't change. It's not a more difficult definition in higher dimension. So let U from RD into R be a given function, and consider the collection of all sets, all open sets in RD, which we denote by omega I, such that U is equal to 0 almost everywhere on omega I for each I in this collection of indices. So this collection of indices is arbitrary, and these are just all the sets where your function is equal to 0 almost everywhere. Then we define the support of U. Sorry, I wrote F here, it should be U. We define the support of U as, so you take the union for I ranging in this set of indices of all the omega i's, and then you take away this union from RD, and this is defined as the support of U. So we are just looking at all the sets where U is 0 almost everywhere. Then we take the union of all these sets. So in the resulting set, my function U will always be 0. And then we look at the complement. So morally speaking, the complement should be the set where U is non-zero, right? And we define this to be the support of U. So first remark, without proof. The above definition makes sense, since it is possible to show the following facts. So if U, fact number 1 is that U is equal to 0 almost everywhere on this union, as I was mentioning before. So it is possible to show this. Fact number 2 is that if U1 and U2 are equal almost everywhere on RD, then the supports are the same. So this is exactly what we were looking for, because this condition is saying that U1 and U2 belong to the same equivalence class, and if this happens, then we have the same support. And which was the property that we were looking for this definition of support. And property number 3 is that if U is continuous, then this new definition of support coincides with the old one. And here I just wrote it down for as a reminder. So the support of U, whenever U is continuous, can be either written in this way, which is definition 7.3, or in the old way, so the closure of the set of points where U is non-zero. An example, so let's go back to the counterexample we saw a few minutes ago. Again, we consider U to be the characteristic function of the rational numbers. And since the Lebesgue measure of the rational numbers is 0, we know that U is equal to 0 almost everywhere on R. Therefore, since it is 0 almost everywhere on R, whichever open set we take in R, we will have that U is equal to 0 almost everywhere on this open set. Therefore, basically, we can take just the largest open set, which is R itself, and we have that the support of U, according to the new definition, is R minus the union of these omega i's, where U is 0, but this union is none other than the whole real line. So in the end, the support is R minus R, which is the empty set. And clearly this coincides with the support of V, where V is the identically zero function. So in this case, the support behaves in the way we would like. So the support of a zero function is empty, as it should be. And if we change this zero function on a set of measure 0, as we did in this case, the support doesn't change. And obviously this does not contradict 3 because u is not continuous. Okay, so this u here is not continuous, and so we cannot expect the support of this function to coincide with the classical support. However, this function is continuous, the constant, and so we saw before that the classical support of this is the empty set, and you can also check that with this new definition, obviously the support will be the empty set, so the two definitions coincide for V, which is continuous. Okay. So we define the support because it's in the future for technical tasks. It will be very useful to estimate the support of a convolution, and the estimate can be achieved as in the following proposition. So proposition 7.4 says that if U belongs to L1 and V belongs to LP, for some p between 1 and plus infinity included, then the support of the convolution is just the closure of the algebraic sum of the supports. So support of U plus support of V closed, where this sum is defined in the usual way. So given two sets in R, E and F, we define E plus F as the set of all vectors x plus y, where x belongs to E and y belongs to F. Okay, the proof of this proposition will be left as an exercise for the exercises course. Okay, let's move on. Okay, so why we introduce convolutions? We do that because they are very useful to smooth functions. So basically what happens is that if you have, say, an L1 function and you convolve it with another function which is smooth, the convolution between the two functions will result in a smooth function. And okay, maybe this is not the only way to smoothen a function, but the point is that convolutions are very handy because if you smooth a function by convolution, basically you can produce a sequence which is converging to your original function in a good way, as we will see in the next results. So first we need a definition of local integrability. So let omega in Rd be an open set, MP between 1 and plus infinity. We say that a function from omega into R is locally integrable in omega if U times the characteristic function of K belongs to LP whenever K is a compact set contained in omega. And the space of locally integrable functions in omega is denoted by LP loc. So LP locally integrable, this means. Okay, I mean, this is just saying that, for example, if you take a constant function and omega is the whole real line, then you know that unless the constant is 0, this constant function does not belong to L1, for example. However, if you look at this condition, whenever you multiply the constant by the characteristic function on a compact set, then you get that the integral is finite, because it is just the measure of the compact set, which is finite, times the constant. So in that case, the constant belongs to LP loc, L1 loc, but not to L1. Okay, and we are remarking this here. we have that LP lock is contained in L1 lock for all open sets omega and all exponents p, of course. But remember that this is not true for the LP spaces if omega is unbounded. So the LP spaces are not nested if omega is unbounded. However, this inequality, this inclusion rather, holds for LP. So if you remove the locks here, so this holds for LP if omega is bounded. And so, okay, we come to this theorem, which is the main reason why we introduce convolutions for their smoothing effect, as I was saying. So point A says that if U belongs to is continuous and compactly supported in R, and V belongs to L1 lock of R, then the convolution between U and V is well defined for each X in R, and also the convolution belongs to the continuous functions. So U continuous and V L1 lock, and the convolution is continuous. So it looks like this convolution is taking the regularity from U, where B is not regular at all. I mean, this is just, if you think about it, this is just a measurable function with finite integral, and instead this is telling you if you convolve this function with something more regular, you get the same regularity. Okay, but then maybe we can prove it also for something similar for C1 functions or CK functions. And indeed, this is what point B says. So let k larger than 1 be an integer, and U be a CK function compactly supported, and V L1 lock. Then the convolution belongs to CK, so the convolution is k time continuously differentiable, and the derivative is given by this formula. So this function is k time differentiables, and the derivative here is just given by the convolution between the derivative of U, so the kth derivative, convolved with B. So what's happening here? Again, B is just L1, but U is CK, and then the convolution becomes CK. And if you want to derive this function here with respect to X, then basically you just pass the job of the derivation onto the regular function, which is U in this case. So the derivative of a convolution is just convolving the kth derivative of the regular function with V, which is the non-regular one. And this is exactly why, I mean, convolutions are very useful, this property here. In particular, as a consequence of B, obviously k is arbitrary, so if you have a function U which is C infinity and compactly supported and V is in L1, then the convolution is itself a C infinity function. And this formula here holds for every order of derivation k. And again, the proof of this theorem will be left as an exercise for the exercises course. They're not too difficult, they're just, I don't know, very technical, so I would rather do something more more interesting in the lectures, and then leave you the technical details for the exercises, because I think it's good to see these proofs at least once in your life. Okay, let's introduce mollifiers. So a sequence of mollifiers is any sequence of scalar functions such that these properties hold for each n. So the first property is that rho n is a C infinity compactly supported function The second property is that rho n has to be non-negative, with support contained in an interval around the origin. So the interval is closed here, and it's minus 1 over n, 1 over n. And then we also want that the integral of this function in the whole R is just 1. Okay, so this is called, whenever a sequence of functions satisfies this property, this sequence is called mollifier, standard. Not standard, but mollifiers. So we see here an example, which is the one of standard mollifiers. And maybe we saw this already in the beginning of the course. Actually, we saw the example of this function here. So we consider rho as the scalar function, which we already defined in remark 3.2, but as a reminder, I redefined it here. So this function is just c times the exponential of minus 1 over 1 minus x squared, if x in absolute value is less than 1, and 0 otherwise. So, and the picture is this one. So this is the graph of rho. And as you can see, clearly rho is, I mean, not clearly, but you can show that rho is c infinity, and the support instead is clearly given by this interval here, minus 1, 1, and also rho is evidently non-negative, and this constant c here is chosen so that this integral is equal to 1. Okay, so c is just 1 over the integral of rho on the whole real line. Okay, given this function here, the standard bump function, we can define a sequence of mollifiers just by rescaling. So rho n of x is defined then as n times rho evaluated at nx. And so you have to imagine that the profile of the resulting function is just this one. So what we are doing is we are rescaling the spatial variable. So basically what you have here is getting closer to 0. So this function is squeezing around the origin, and you see the support becomes minus 1 over n, 1 over n. But at the same time we are increasing the height of the function, and the maximum value here becomes n c over e, whereas in the case of n equals 1, so the original function rho, the maximum is on c over e. So what is happening more or less is that this function is converging pointwise to the identity, sorry, to the zero function for n that goes to infinity in all the points which are non-zero. So here and here, so r minus 0, the function is converging to 0 because pointwise, as you can see, if you're sitting this point, for example, and you wait long enough, so for n sufficiently large, this support will the support of rho n will be inside this smaller interval here, and so your function will be 0. And instead at 0 the function is exploding, so this function evaluated at 0 is going to plus infinity, because if you evaluate rho n at 0 you get this value, which goes to plus infinity as n goes to plus infinity. Okay, and here I didn't write the property, but this is a sequence of mollifiers because you can check that it satisfies these three properties here. Okay. And yeah, the rescaling here is done, so we rescale both the support and the height, because in the end we want the same integral. So what you can check is that the integral of this function rho n is the same as the integral of rho, so they're both equal to 1. Proposition: if you have a continuous function and rho n is a sequence of mollifiers, then if you take the convolution between the two, the convolution is converging to U uniformly on compact sets as n goes to plus infinity. So this means that for each compact set fixed in R, you have that if you look at the maximum for x in the compact set of this difference of rho n convolved with U evaluated at x minus U evaluated at x in absolute value, then the limit of this quantity has to go to 0. So this is just saying this is the uniform norm of rho n convolved with V minus U on the compact K, and I'm just saying that this uniform norm has to go to 0 as n that goes to plus infinity. So as you can see, this is your first hint to the fact that convolutions are useful, because here I'm saying that if I take something continuous and I convolve it with rho n, which is C infinity, then by the proposition before I should get something which is C infinity, and by this proposition, so I obtained a C infinity function, which is this one, which is converging uniformly on compact sets to the original function, which was just continuous. So I'm just approximating U by something much more regular, C infinity in fact. Okay, the proof of this proposition is again left for the exercises course, and we pass to an approximation theorem in LP. So here the approximation was done for continuous functions. Now we take something in LP for P between 1 included and plus infinity excluded, and rho n is a sequence of modifiers. Then you can prove that rho n convolved with U is converging to U strongly in LP. Okay, so this is very nice. Here I had something continuous, and I found that the convolution with modifiers converge uniformly on compact sets. Instead here you have something which is LP, and I find that the convolution converges strongly in LP. So as you can see, this is very nice for approximation results, because here, for example, I am producing a smooth function which is converging strongly to my original function in the right space, so with the right topology. And okay, theorem 7.9, we are going to prove it in this lecture. So start by fixing epsilon larger than 0. By theorem 6.16 in the appendix on LP spaces, we know that the continuous and compactly supported functions are dense in LP. So this means that there exists U tilde in the compactly supported functions, such that U minus U tilde with respect to LP norm is smaller than epsilon. Okay, then by proposition 7.8, we know that since U is continuous and compactly supported, then the convolution between the standard modifiers actually, sorry, and U tilde is converging to U tilde uniformly on compact sets. And also we know that by the proposition on supports of the convolutions, that the support of this convolution here can be estimated, so this is contained in the closure of the sum of the support of rho n plus the support of U tilde. Now, by definition of modifier, this support here is just the interval minus 1 over n, 1 over n. And so this quantity here, this set here, sorry, is contained in support of U tilde plus minus 1 over n, 1 over n. And this is true for all n in R. So in particular, this interval here is always contained in minus 1, 1. So therefore we conclude that the support of this convolution is always contained in support of U tilde enlarged by this interval minus 1, 1. In particular, so let's scroll down, sorry. In particular, the support of convolution rho n times U tilde minus U tilde, this is contained in the support of the convolution union the support of u tilde. I mean, this is sorry. This you can easily check by hand, this inclusion here. And for what we proved above, this one is contained in this set here. And so we get this second inclusion. And so here I'm just doing -1, 1 plus the support of u, union the support of u. And this is just the... I'm basically not doing anything in this union because, I mean, in particular this set here, since this interval contains 0, then this algebraic sum here contains the support of u. So if I do the union with the support of u tilde, I'm not doing anything. And I end up with the same set, which we define to be k. And notice that k is compact because u tilde, sorry, was compactly supported, and this is compact. And the direct sum between not the direct sum, but the sum between two compact sets is compact. Okay, now we need to estimate the LP. So we need to show that this guy here, rho n convolved with u tilde, is converging to u with respect to the LP norm. So let's just estimate the LP norm of this difference by 2. This is equal to okay, not the same thing, but okay, by 2 was this estimate here. So the support of this guy, which is given here, is contained in this set k, as we showed in 2. So it means that this this quantity here is 0 outside of k. So I can just the integral disregards whatever happens outside of k, and I can just look at the integral over k. And on these compact sets here, I can just take out the infinite norm of this quantity. So this is the maximum for x in k of this difference here. And then I'm left, if I take outside this quantity from, so this quantity here, from the integral, I'm left with the integral of 1 on the set k, and this is just a measure of k. Okay, the measure of k is finite because k is compact. So, and also this guy is going to 0 because we know that since u tilde is compactly supported, this convolution is converging to u uniformly on compact sets for the proposition we stated before. And therefore the right hand side of here, this right hand side here is going to 0, and proving that this integral is going to 0 as n goes to plus infinity, which is exactly our thesis. So we just showed that the convolution between rho n and u tilde is converging to u strongly in LP. Okay, but then we are basically almost done, because so this was our thesis for but for the case of u tilde compactly supported. We need to show this condition when u is only LP. And how do we do it? We know that compactly supported functions are dense in LP. Then we can just use an approximation argument in conjunction with the knowledge of this fact here for continuous compactly supported functions to conclude. So we're going to do exactly that. So notice that the modifiers belong to L1 with norm given L1 norm is equal to 1, and this is by definition of modifier. And also the difference between u and u tilde belongs to LP, because this is continuous, this is in LP, then the difference is still an LP function. And therefore by Young inequality, which we proved last time, we obtained that the p norm of the convolution between rho n and u minus u tilde can be bounded by the 1 norm of rho n times the p norm of u minus u tilde. But this guy here was equal to 1, so in the end we are just left with the norm of u minus u tilde here. Okay, so now by the usual adding and subtracting, so we start with the quantity we want to show. It is small, so this is rho n convolved with u minus u, where u was our original function in LP. Then this is less or equal than rho n convolved with this difference plus rho n convolved with u tilde minus u tilde plus u minus u tilde. And here I'm just adding and subtracting what exactly, let's see. So this guy I had originally, and also this guy I had originally, so I'm just adding and subtracting these two, this one and then this one, and I'm doing twice the triangle inequality. So this first term here can be estimated by this Young inequality, and I'm just left with the difference in LP between u and u tilde. This guy I don't estimate for the moment, and also this guy stays the same because I mean it's just the same as this one, so we're just going to sum them up. And so in the end I'm left with our quantity, the quantity of interest can be estimated as such. Now remember that u tilde was chosen so that the LP norm, so this is an LP norm, I forgot to add a p here, so was chosen so that the LP norm of this difference is smaller than epsilon. Okay, so here I can just put 2 epsilon, and for the second term here we know that this goes to 0 because this was the condition triple star that we proved earlier. So in total, if we take the lim sup of this quantity, so lim sup of rho n convolved with u minus u, then this is less or equal than the lim sup of this quantity here, which is equal to the limit of this quantity because this is a convergent sequence, and we know that this is going to 0. So in the end, the lim sup of the quantity of interest is less or equal than 2 epsilon, and also epsilon was arbitrary, so epsilon was arbitrary, and here there is nothing depending on epsilon, so we can just choose epsilon equals to 0 basically. And we conclude that, I mean, to be precise, we don't choose epsilon equal to 0, epsilon has to be greater than 0, but here we are saying that this is something positive, or non-negative rather, which is smaller than an arbitrary quantity, and since the quantity is arbitrary, then we conclude that this guy is 0. So the lim sup of this is 0, and concluding that the limit is 0 because I mean we just showed that lim inf is larger than 0, then lim inf is smaller than lim sup, and lim sup is going to 0, then it means that the limit exists and it's 0. And so in the end we showed that rho n convolved with u minus u is converging to 0 in LP, which is our thesis. Okay, corollary. If I is an open set in R, so possibly unbounded, and if P is between 1 included and plus infinity, then the C-infinity compactly supported functions on I are dense in LP with respect to the LP norm. So okay, I was contemplating if doing whether or not doing the proof of this corollary. I mean, I originally wrote it down in the notes, but I think it doesn't add anything to the course actually, so I'd rather spend the time to do something more interesting. So please just ignore the proof of this corollary. We won't include it in the program of the course. And as I was saying, let's move on to something more interesting, which are the fundamental lemma of calculus of variations and DBR lemma in LP. Okay, so we are now fully ready to proving these two lemmas in the LP setting. Let's start with the fundamental lemma of calculus of variations. So let I in R be an open set, so could be bounded or unbounded, and suppose that U belongs to L1 log of I, and is such that U times V integrated over I is 0 for all the C infinity compactly supported functions on I. Then, as we already concluded for continuous functions, also in this case we have that U is equal to 0 almost everywhere on I. So obviously this is the difference with the continuous fundamental lemma of calculus of variations we saw at the beginning of the course. In that case we concluded that U was 0 everywhere because U was continuous. In this case we can just conclude that U is in the same equivalence class of the 0 function, so U is 0 almost everywhere. But this will be enough for our analysis. I mean, in the sense you cannot expect more. This is actually all you can prove. You can just prove that if this holds, then U is equal to 0 almost everywhere. Okay, let's look at the proof. Okay, let psi, capital psi, be L infinity and be such that the support of psi is compact and contained in I. And then consider psi n to be the convolution between psi and a sequence of modifiers rho n. Then by the proposition on supports, we know that the support of psi n, which is defined as a convolution, is just contained in this set here. So this is the support of the modifier rho n, and this is the support of our function psi. Therefore, since this is compactly supported, since this is compactly supported and the support of psi is contained in our original set I, and since this is becoming small, it means that there exists some n, capital N, such that this support here is contained in I for all n sufficiently large, so larger than this capital N here. Moreover, we know that since these are modifiers and this is an L infinity function, we know that psi n belongs to C infinity by theorem 7.6. As psi n is defined as a convolution, and theorem 7.6 is telling us that convolutions have a smoothing effect, so you end up with something C infinity. Okay, so psi n is C infinity, and here we just said that the support of psi n is compact and contained in I, so it means that psi n is compactly supported C infinity, and so by assumptions we know that so psi n becomes a test function for this condition here, this one here. So in particular we know that the integral of U times psi n is 0 for all n sufficiently large. Okay, so now notice that psi is L1 since it is L infinity and also compactly supported. Therefore, by the theorem on approximation for convolutions, we have that psi n converges to psi strongly in L1. And therefore, up to subsequences, we have that psi n converges to psi pointwise almost everywhere in R. And this result is given in proposition 6.13 in the appendix about LP spaces. Moreover, by Young inequality, we also have that psi n, which is a convolution. So the L infinity norm of psi n is less or equal than the L1 norm of rho n times the L infinity norm of psi. And by construction, the one norm of rho n is equal to 1, so in the end we can bound the L infinity norm of psi n with the L infinity norm of psi. Therefore we can invoke dominated convergence and pass to the limit in star. Okay, because what's happening? So we just said that psi n is converging to psi pointwise, So u times psi n converges to u times psi pointwise. And also we know that we can bound this quantity in L1 with the you can bound this quantity here, this function u times psi n in L1, with the one norm of u times the L infinity norm of psi, because of this estimate here. And so these are all the assumptions we need for the dominated convergence, meaning that we can pass to the limit in this integral here and obtain that this one is converging to the integral over I of u times psi n, and since this is 0 for all n, we also conclude that the limit must be 0. So u times psi is equal to 0. Okay, so if we go back, we discover that we just proved that for any L infinity function which is compactly supported in I, then we have that u times psi is equal to 0, integrated, of course. So now let's choose let's choose the function psi in a clever way. So let k contained in I be compact. We choose as function the following. So psi of x is defined as the sine of u of x for x in k. So this means that psi is equal to 1 if u is positive, and psi is equal to -1 if u is negative. And so this is in k, and instead we set psi to be 0 outside of k. Therefore this function satisfies must satisfy 2, because psi belongs to L infinity, and the support is given exactly by k, which is contained in I. So psi is L infinity and compactly supported in I. Therefore from star we get that this integral here, integral of u against psi, this particular one, is 0. But also by definition we know that psi is 0 outside of k, and it's equal to the sine of u inside of k. So this is the integral over k of u times sine of u. And now you can check that u times the sine of u is exactly the absolute value of u. So we just proved that the absolute value of u integrated over k is 0. And this means that u is equal to 0 almost everywhere on k by the properties of the Lebesgue integral. You can see the remark after theorem 6.4 in the appendix on LP spaces for the statement of this fact. So u is equal to 0 almost everywhere on k, but k was an arbitrary compact set contained in I, and therefore we conclude that u is equal to 0 almost everywhere on I, which was our thesis. So okay, now we established the fundamental lemma of calculus of variation in LP, and we pass to prove the Dubois-Reymond lemma in LP, and we do it in the second part of this class.